So it's here presenting you my work. So this paper title is Indium Phosphide RTD Detector for Terrace applications. And I don't know if you're familiar with the RTD, but it's a very special device. It's a diode. And in this particular case, we have a triple barrier RTD. So RTD with 3 potential barriers. And it's basically the behavior and the working principle is illustrated here. And the special thing about this diode is that its conduction mechanism is based on tunneling current. So we are talking about tunneling current. And this makes it very special compared to a thermionic device such as the Schottky diode, because we can get very high curvature factors of the IV curve, which makes it very important for terrace detection. We can get, for example, curvature factor of 15 and 27.3 around the zero bias region. And in this case, for this work, we basically used a half a micrometer squared triple barrier RTD embedded in the ground signal ground structure. And the goal was to characterize its detection capability in the WR2 band, so 500 gigahertz. And this is the measurement setup that we used. So we injected the terahertz power through a frequency extender, an actor analyzer, and through GSG probes, basically. This is how the fixture structure of our diode looks like. And basically, we could measure the rectified DC voltage. And this voltage is then translated into responsivity. Responsivity parameter is one of the key parameters of the detector. It's basically our output, DC output, divided by the input power. And yeah, as you can see, the results are, let's say, pretty good. So we are above 1000 watt per watt. And but the other very important parameter for terrace detection is the detector sensitivity, which goes together with the responsivity. But the sensitivity is measured through the noise equivalent power. And this also takes into account of the noise properties of the detector. So we are interested to know what's the intrinsic noise contribution of the detector and how it relates with the responsivity that we calculated before. And of course, the lower the noise, the better the sensitivity. It's sort of a signal to noise ratio thing. So that's how you should see it. And so we are interested in diodes that exhibit very low noise and very high responsivity. In this case, we can get very low NAP, basically. And for this diode, we got NAPs around, let's say, 2 picowatt per square root of hertz, up to 500 gigahertz. And I would say it's a nice result because this puts it really into, say, in a good comparison with the other state-of-the-art for terrace direct detectors. Thank you.